Okay, so let us continue. You can see my screen, eh? What I'm sharing. Can you see it?
Yeah.
Because I cannot see it from my side. Are you able to see it?
Yes, I can see it.
Okay. That's okay. So let's continue. We continue with our study on how to write zero knowledge proofs in Noir. So today we'll be looking at zero knowledge modular exponentiation circuit. So we know what modular exponentiation is, and we know where it's applied. For instance, when you're proving knowledge of x and e, that you know x and e, x raised to e, you know x and then you know e, so that such that y equals to x raised to e mod m. So this is what we call modular exponentiation. So it's applied in very many areas. So we can apply this in, it's used in RSA, it's used in Delft-Hellman, it's used in El-Gamal signatures and so on. So there are many areas this can be applied. So if you wrote it properly, then somebody who wants to do El-Gamal signature can borrow from you, and or you can even begin from this. You can write a smaller thing like this. Then from there, you advance it to do El-Gamal signatures, to do RSA signature, and so on. So you can always advance these circuits to do more than what they currently do. So I've said modular exponentiation is very key in cryptography, and because of these applications, these are the areas you can apply this knowledge. So proving knowledge of x and y such that this is true mod m, where m is a prime number. M, you can make it a prime number without revealing x and e. So the prover will only, the verifier will only know what y is and m, but it's not supposed to know what x and e are. It's only the verifier, the prover who knows this, all of them. But he wants to prove that he knows x and e without revealing what they are. So Noah then would assist us to write this. Of course, we have various languages that can be used, but Noah does it easily, in a very easy way, to write this circuit, zero knowledge proof. So our goal, we've already stated what it is we want to build a ZK circuit where the prover proves knowledge of x and e, so that y equals to x raised to e mod m. The verifier will only know what y is because y is public, but will not know x and e. So this will be our inputs. We've made them to be U32. You can always increase to bigger value. You can do it U64. But U32 is okay. It's okay in cryptography. You can use it. But if you want a slightly bigger thing, you can use U64, which will also work. Even U8 works, and it works very well. Now, so I'll use a branchless modular exponentiation. Branchless, so that means, what I mean by that is I'll avoid things like if and then conditions. Those conditions is what I'll avoid in this this circuit. And there are advantages for avoiding those conditions. There are advantages, and of course, I list some of the advantages why. Oh, you had muted me.
Oh my God, that must have been, I clicked the wrong button. Sorry about that.
But you can still see my screen. Is that okay?
Yes, I can see your screen.
Okay. So I was saying that the advantages for using branchless model exponentiation, and I've just said what branchless means. In other words, I'll be avoiding conditions like if and then in this circuit. Now, so the circuit is this. This is the circuit. So I'll explain again what each of these function does. We have this first function. This first function says is function mod exponentiation branchless U32. And of course, I've said what branchless means. So we begin we begin by making the exponent to be mutable. That means it be varying from time to time. So the exponent, okay, the exponent is U32, but it will be varying. And again, our modulus will be U32, and then the outcome of those of the exponent raised to x, the outcome will be U32 also. Now, this condition here, this one ensures that our mod is not equal to 0 at any given point. So this one must be there, just to ensure that the mod is not 0. So the mod can be any other value. Of course, we've said in this, this example, we would prefer our mod to be a prime number, but any number would still work so long as it's not equal to 0. Now, the result, you see, what we want to do is we want to do x raised to e, and we want it to be y. So this is our result. This result, we make it mutable, and initially we let it to be 1, and it will be changing from time to time until we get the exact value. And our base is the remainder. So every time we do that, so this is what we'll be doing. The new base will be the original base divided by the mod. So the remainder of the original base on the division by mod gives you the new base. So the base also will be mutable, so it will be changing from time to time. And of course, that is what we stated here. At this point, we said let the base be mutable. So we begin by supposing the base, supposing we begin by 2, what I mean by that, and supposing.
I have a question. Sorry to
Yes.
interrupt. So all of these inputs are public or private, like the base, the exponent, the modulus. They are private, right?
Yes, the only thing that is public here is the result.
Okay.
The result and the mod. Oh, okay. This is not the main. This is not the main function. The main function is the one that will define which ones become private and which ones become public. This is just one of the functions that will be helping the main function. But the main function, I'll show you, it will now be defined. This is the main function.
Okay.
Yes, this is the main function. So you can see that X here is private, E here is private, and then M is private, but now Y is public.
Oh, perfect.
Y is, yes, that is the result. So you define what becomes private and what becomes public in the main function. So the other one is just a function that is assisting this to perform the arithmetics. The one that is performing all the arithmetic. So this one now compiles those together and gives the result. So it's this that now you give which one becomes private and so on. But this other one is just a function doing all the calculations. Now, so the base, as I've said, the base in our case will be X and the exponent is that. And we want to do this mod, M, our result is supposed to be Y. So we've said this base will be mutable. Of course, you're giving it some input, but now how does it calculate? How it calculates is what I'm explaining now. You have given it a base, you have given it an exponent, you have given it a model, but it's not using those ones to do calculations just in one step. So the steps are several steps until you arrive at the final answer. So that is why the base will be mutable. The exponent must also be mutable. The modulus is not mutable because that one is a constant. And then this means the result. Okay. Now, so about the result will be mutable, but you begin by letting it be 1. And then the base will also be mutable. But now you begin with the original base you gave it. Supposing your base is 5 that you gave it, it begins with that. But now it will get the second base, the next base. Now, so the next base will be this base. The next base will be the base you gave it divided by the modulus, the remainder of that. The remainder, when you divide the modulus in that base, what remains is what becomes the base for the next round, and so on. So that process continues like that. Now, so I've avoided the branchless. If I had the branchless, I would have said if or for, so that you know how far are you going to work with the base, when are you stopping, and so on. But this one you don't require that because I've given all the steps to the last bit. Now, so this one you're using bits, and you're saying let bit, so the bit will be the exponent, and then 1, and then we have the multiplication result times that, the remainder of that on division by modulus. And then the result will be what you get here, what you get there times that bit that you got there, plus the result multiplied by 1 minus the bit that you got at this point. But I'll explain all this in other slides just to be after this. I've given a slide just to explain how this works. And what is happening in the base is here, what is happening in the exponent is there, and so on until you arrive at the result. That is how the code will be working. Now, I had said I'm working with branchless, and I've said why branchless. And I'm saying branches, which includes if, else, will be expensive in ZK circuits. That is, they would increase constant count. So that makes them expensive. This method that I've used avoids these branches, and that then uses bits just to do the calculation and get the result. And I've said this method is efficient because of that. When you reduce branches, the cost you'll be reducing even the cost in terms of gas and so on. Now, so this is the main circuit, and as I said, this is now where we define which one becomes public, which one becomes private, the way I've just done. So, okay, that's how we do it. And then I've defined which one is a private. You can see X is private, E is private, M is private, but Y is public. So this one, anybody should know that, even the verifier and the prover should know that, but the rest, they should not. And I've said this is a very important step to ensure that your mod is not equal to 0. So you must include that. If you remove it, it will still work. But if somebody was to put a mod that is 0, because you are doing division by mod, your circuit will have to panic. So when you put assert mod M not equal to 0, that means somebody cannot put M equals to 0. So if he was to put that, your circuit will not panic because it will not accept 0 as a mod. But if you did not put this, it will accept 0 as a mod, and then it panics and fails to compile. That is why it's good to include it. Now, I've said before, it's good to be including tests. Tests always, what they do, they test your main function just to ensure that your main function is working as designed. Otherwise, you can have a main function, you do compile, it compiles, you do execute, it executes, but it cannot do whatever thing you asked to do. So it's always good to give it tests so that you can see it all actually is doing what you intended it to do. So I've put some tests in our circuit, and we'll be seeing the circuit. To perform for us 5 raised to 3 mod 17, and it's supposed to give us the correct result, 6. 5 raised to 2 mod 17 is supposed to give us 15. And if I ask it 5 raised to 2 mod 17, this is 16. Huh? No, 4 raised to 2 is 16. Okay, it's supposed to give us 16. Okay, the way I've designed it is I've designed it such that I've not given it 16, I've given a different value. So if I've given it a different value, it's supposed to fail because it's supposed to know that 4 raised to 2 is 16. So if you give it 15, it's supposed to fail. But now in Noir, we don't want it to fail such that the circuit panics and says it fails. No, we want it to pass. In Noir, we always want it to pass. We give it a wrong figure and then say test should fail. So if you say test should fail, it means the program is supposed to understand that you have given a wrong figure and you accept that it's supposed to fail. So in that case, it passes. But if you give it a wrong figure and you don't say test should fail, then it means you want it to panic. And then it does not compile. It panics and then it does not compile. But if you give it, so for instance, I know that 3 raised to 3 is 27. If I just leave it like that and say Nago compile, it will panic. It will panic and stop. But no. If I do this, if I say 3 raised to 3 is 29, and say Nago compile, this is supposed to panic. But I should say I know that this is wrong, so I should say test should fail. So if I say Nago compile, since I've already told it that this one will fail, it then passes. It passes without panicking. And I think at this point we know all this because this is what we've been doing this. So it's not something new. Now, so let me just let me look for the code, and then we try to. I don't know whether you cloned it.
Yes, I cloned it. I have it locally.
Okay. So just share your screen therefore.
Okay.
Which one did you clone?
The modular exponentiation one.
Yes.
Okay. Just a moment. Can you see my screen?
Yes.
You're seeing here, my cursor is moving.
Yes, I can see.
Okay.
Now, so let's begin. Oh, this is the main, eh? Okay, so yes, I can see the notes above. The notes above, just explaining what this is all about. Says model exponentiation using branchless right to left binary method. Returns base raised to exponents. Modulus as a field element. All inputs are U32. That is okay. Now, so we can see that function. It says this is a function mod exponent branchless U32. Then we have the main function just below. And the main function, that is where we've defined what is to be public because this is zero knowledge proof. So it means the verifier is not supposed to know what we've decided to be private.
Okay,
so let's look at our tests. The first test there should pass. I've said function test pass. Now, I don't know whether you've discovered that when you write these functions and repeat the wordings, for instance, you can see in the first test I've said test pass case 1, and this other one is case 2. So if you write case 1 twice, if you write case 1 twice, even if the tests are different, it will fail, it will not pass. For instance, just try and change that 2 to 1, and then say Nago test and see whether it runs.
Okay, so I changed these 2 to 1.
Just write it as 1. and then say Nago tests.
All right. Nago test. Oh, okay. I need to go into circuits. CD into.
Oh, yes. It's CD circuits.
Yeah. So
Nago
it says
test.
that
What does it say?
it says that duplicate definitions of function with named test pass case one
Yes.
found.
Then on the left, it tells you that line 32 has the first, then line 41 has the second. That means the terms, the wordings have been repeated in line 32 and line 41. So it cannot run if you try to repeat anything. Okay, return that as 2.
Okay. Here.
Okay, so that is one thing we've seen. We've seen that, of course, we always write hash and then test in brackets, those square brackets. If the test is meant to pass, there's nothing you add. But look what number 3. This one is supposed to fail. So you say test must fail. Now, this is different from Rust. What Rust does not have should fail. What Rust does, if a test is supposed to fail, they would just comment it out so that it runs without failing. So that your program runs without failing, comment it out. But for now, you don't comment it out, you write should fail. So what this one is doing, we have 4 raised to 2. 4 raised to 2, you know, the answer is supposed to be 16, but I've written there 5. I've written there 5. So that is supposed to fail. So when you say Nago test, it runs.
Yeah, it does run.
Yes. It tells you that 5 tests have passed. Is that okay?
Yeah.
But now delete the bracket of should fail and let's see whether it runs.
I delete this.
Yes, there's no problem. No, not that one.
Which one?
Not that one. Inside the bracket, after test, just after test. After test,
okay.
test
After test. Okay.
Yes. That is a command that is telling it to run. Just
So
delete, delete should fail with that bracket.
All right.
Yes. Now run it.
Yeah. One test has failed.
Yes, it has panicked. It has, and you see, we avoid this. We avoid this. We don't want it to panic because it's a program that is online. So you don't want people to put for some inputs to make it to panic like that. You want it to run continuously. You get the point.
Yeah.
Yeah, so it should not panic. It should run continuously. So for you to avoid that, if there is a test that you feel should fail, you tell it that this should fail. So if somebody were to input that, then it's supposed to fail. So what I was saying, what they do in Rust, they don't have that option. They comment out. They comment out. So just comment out the rest of beginning from test, just comment it out.
I comment this whole test?
Yes, the whole thing. The one that you deleted. How do you comment it out? Oh, you just did it once, huh?
Yeah,
okay,
okay.
Now run it. It should run now again.
Oh, let me save it. Yeah. So 4 tests
Yeah,
have
so
passed.
yes. So if you do that, it's also supposed to pass. But now if you do that and then submit your PR, it's not be accepted because Noah has already defined how its circuit, how its tests are supposed to be written. So if you try to comment it out the way first, they will reject that. So now undo.
Undo the
Yes, yes, undo that.
okay. I think it's missing a curly, yeah, like that.
Yes, yes, just close it. Then return should fail.
Okay, it was right here.
Just a bracket, yes, should fail. Underscore.
Okay,
It
so
should, and then underscore fail.
underscore fail.
Okay, run it again.
Yes, so 5 tests have passed.
Yes. Now, so when you are testing, you try and test as many scenarios as possible. I was like, when you check my first example, let's just look at the first example. No, the first test, what is it? Let's look at the first test.
This one.
Okay, so that one I took 5 raised to 3. It's mod 17. So I get the correct result, 6. Then again, the second one. So the second, let me check the second one. It is 7 raised to 2, mod 17, it's 15. Now, so I've checked those which should pass. So now I try which one should fail. I try now if I give a wrong result. So this is a case where I've given the right result. What about where I'm giving a wrong result? 4 raised to 2, I've said the result is 5. That is wrong, should fail. This other one, now I'm testing if the modulus is 0. And remember, above, I've already said omit 0. Modulus should not be 0. Is that okay?
Yeah.
So I'm testing what it should fail. That is why I've said in bracket, I've said that it should fail. Because our circuit, we said that it should not accept mod of 0. Should not accept. So that is already in the circuit defined above. So I come and test. Supposing somebody was to put mod 0. No, if you run, I've already said it should fail. That means if somebody puts mod 0, it will not panic.
Yeah.
It will not panic. Okay, so I've already tested that. Then I come and test large exponent. So I try a very large exponent and I want to see whether it can perform that. And again, it does perform. So when you are writing a test, try and test almost every scenario and see, especially areas where you think it may panic. You try and test and see it does not panic. So that if it doesn't, then it means your circuit is okay. Now, so we don't have target. Is that okay?
Yeah.
We don't have target, so let's have it so we can do Nago compile.
Okay.
Okay, now target gives us witness, and it has written some. What does it written after compiling? Up or down? What did it say? Not
no, nothing. Didn't tell me.
Oh, just compile and
yeah.
It's okay. Okay, so but now that is a witness.
Yeah.
What is it named?
It's named Noir Modular Exponentiations .json.
Yes. Okay, so now let's look at our prover dot toml.
Yeah, we have. Yes.
Okay, so that we are giving it some of the inputs. We're giving it an example of an exponent, an example of a mod, an example of an x, then an example of a result. So, and it must be correct. So just, it's not that you should give it only this. You give it just an example of what you expect it to do. Supposing E is 3 and M is 17 and X is 5, you expect the result to be 6. Now try and give it a wrong result. Give it 5 there where there's Y. Now run. Now go execute.
It does not. It says that this condition has not been.
Yes.
Yeah.
The condition has not been met because our condition was that if you give it an X, an E, an X, and an M, is supposed to give you the right Y. Now, try now go test. Try now go test.
Okay. But the test still passes.
Yes, yes. Even compile, try to compile. Now go compile.
Yeah, it compiles with no error. Yeah.
Yes, it compiles without error because compile and test has got nothing to do with execute. Execute is supposed to assist get the proof, not the proof, the verification key is a way of trying to get a verification key. So you are beginning from execute as you move to get execution verification key. So it must be very correct. The prover toml must be correct. So if the prover toml is wrong, it means the proof you generate will be wrong. So from the very start, it will reject because it will. If it passes, then it shows that you will definitely get a proof, and the proof will be wrong.
Yeah.
The proof will finally be wrong. So this is now to gather on the side of the proof. Compile and the test is just on the side of the circuit to ensure that the circuit is correctly written and is correct. So when the circuit is correctly written, compile will pass.
Yeah.
And then test will also pass if the tests have been written correctly.
Correctly.
Because if you write the test wrongly, compile will still pass.
Yeah.
The compile will pass if the test is wrong. Execute will pass. So each of these has its own area of work. It has its own area. So compile will be looking at is the circuit, is the function. All those functions in the main circuit, are they correctly written? So that is what compile will be looking at. So compile will still work even if the prover toml is not correctly written. And the prover toml will not be looking at the tests. The prover toml is the prover toml execute. Execute looks at the prover toml and then and the main function. The prover toml and the main function. The prover, what is in the prover toml must agree with what is in the main function.
Ah.
Yes, yes. Okay. So if the main function is not well written, execute will not work.
Interesting.
Execute will not work because now the prover toml will be testing nothing. It has to test what is correctly written first of all.
Yeah.
Okay, so return the correct value.
The value was 6.
Yes. Again, do now execute.
Yeah. So we've got the circuit
Okay.
witness.
It says a witness has been successfully written, solved, and it tells you where it has been stored. So it says,
Yeah.
Witness has been saved to target stroke Noir modular exponentiation, and it says dot gz. So that is where if you go to the target, you can see it's there. Okay, delete target.
Okay. Yeah, we deleted it.
Okay. Okay, do dot backslash build.sh.
There.
Is the target back?
Yeah. Oh, yes, it's back.
What is inside?
It has the JSON and it has a verifying key.
Yes, so the build.sh has done that because the way I've written it, it does Nago compile. So just click on it.
Okay.
On the build.sh.
Click
Yes,
on the
there.
build.sh. Okay.
Yes, yes. So you can see the first command as I've told it to do Nago compile. So that is why the target comes back. And the other thing it's supposed to do is supposed to generate verification key and then store it inside target. So you can see that is the second command. The second command I've told it be write verification key. And the command that it's using to write that is the command be write verification key oracle hash kekak b target Noir modular exponentiation or JSON, then target, then and so on. So that is the command. That is just a command. In fact, if you have to take that command the way it is and run it in on your terminal, it will still do the same thing. If you just to copy that, if you are to copy that and run it in the terminal, it will still do that verification key. It will still give you verification key. But now, if it fails, it's supposed to tell you if it fails to generate a verification key. Now, the other thing that it does, that is not, it has two functions. I've given it, no, three functions. The first function I've given it to do compilation, Nago compile. The second function I've given it to write a verification key. Then the last command I've given it is to write the solidity verifier. This is our contract. The solidity, and I told it to write that using the command be write solidity verifier. Then it is supposed to store that under contract and is storing it under contract as verifier.sol. So if you go to the contract, you'll now see this thing called verifier.sol. If you have to click contract.
Yeah.
Yes, verifier. You can delete it. You can delete verifier.sol and do.
Could you explain to me why? What's the use of the verifier.sol again?
That is the contract. Just scroll it to the bottom. Scroll verifier.sol to the bottom. And when you there, you can see contract Hongo verifier. So this is a contract. And this contract is called Hongo verifier. And it said is a base verifier. So this one, it gives you what is inside this contract. So at the above this verifier.sol is just some commands, but it's a contract. This is a contract. So if you are to, for instance, deploy this, this is what you will then be deploying. Yes, because it's the contract.
Okay.
So in now it's just called verified.sol, but you can give it another name, but you give it another name in the command inside build.sh. But conventionally, many refer to it as verified.sol.
Okay.
It's the contract. Okay, delete it.
So I'm gonna delete the verified.sol.
Yes. Okay, run build.sh. It's back.
Yeah.
Yes, it's back. So that is our contract, the solidity verifier. Let's go back to build.sh.
Okay.
And the command that gives us that is that bb write solidity verifier. Just copy that command. Let's see whether it can do it without outside. Just copy the
this command.
No, the second. Yes, there.
This one.
bb write solidity verifier. Just from bb write.
Okay.
bb write.
bb write.
Yes.
That.
Okay. There. Let's go to the terminal.
Okay. Yes, it has saved it to verified.sol.
It has given you that. Is that okay? Just delete verified.sol. Let's see whether it generates it. Okay, run it.
Yes, but it has an
Yes,
error.
it does it.
Okay,
yes,
yeah,
so that is the same command. What we do, as we discussed earlier, we use build.sh just to automate the process of proof generation, verification. You remember the other time we also did automate the key generation and so on. So they are called scripts. They are called scripts, and their work is just to automate the process, so that you are not at every moment copying the command and then running it in the terminal. No, you just need to automate. You come up with a script that can do the whole thing at once. So you can see build.sh when you run it. It did not just do one thing. It did for us 3 things. You can give it as many roles as you want. But for this circuit, I just gave it 3 roles. One was to do Nago compile, and the second one was to do verification key generation, and then the third one was to give me the solidity verifier. If you want, you can also ask it to do Nago execute, and it does Nago execute for you, then produces a witness. You can see at this, we did not have a witness so far. We did not have. For us to have a witness, we require Nago execute. So if you wanted that, you would. You can even ask it again to. You can even ask it to create contracts. You can see, like in our case, we created this contract, that folder contract.
Yeah.
We created manually. But you can ask it to create the folder contract. Then after creating, store the solidity verifier inside that contract. So you can ask it to do all those, and it does for you. So it's just you giving you the command that it should run, and then it does. So we are done with the build.sh. We want to generate the proof. So that means we have to get inside JS. Let's get inside JS on the terminal. Yes, inside JS we have that generate proof .js ts. That is what will be helping us. So where are you?
I'm in JS. Yes, I've stayed it to JS, into JS.
Okay, so that one, to generate the proof, you'd have to do yarn generate dash proof.
Oh, yeah, generation. Okay, okay.
It's just okay. What you've written is okay. Okay. Yarn install.
Okay.
Yarn install. Okay. Once it's done, installation, you can repeat the same command, yarn generate proof, and see whether it generates a proof.
Yes, proof has been generated successfully.
Okay. Done in 1.99 seconds.
9 seconds. That's very fast.
Okay, so where's the proof? It has been written there. The proof is inside target.
Yes, should be inside target here, but we cannot see.
Yes. That's a proof.
Yeah.
That's a proof. Now, a very important thing here is public inputs. Just click on public inputs. And the only public input is 6.
Yeah.
Is that okay?
Yes.
That is why. If you check our prove.tom, yes, 6 was our only public input. Now let's go back to our main.nr. Go to main function.
Main function.
Is it okay? This one, okay. Now, and make that M public. Make M public.
So I should just say pub. Y.
Yeah. Just say pub.
M.
Before you, yes. Okay. Good. Okay. Now run yarn generate proof.
Okay. I think I even command. Yes. So proof generated successfully.
Okay. Check public inputs.
Public inputs.
Still one.
Still one.
Okay, delete.
Or maybe we should delete it.
Yes, yeah. Delete target.
Okay.
Do build.sh.
Yeah, .build.
No, get inside, get outside of JS first.
Okay, so cd into the circuit.
Yes.
And then we go into JS.
Get outside target circuits. Okay. I'll try again. Yarn generate proof.
Okay. Where is our public input? Yeah, now we have 2.
There are 2.
Yes.
So public inputs, and now, now let's go back and delete what we did, because you see, we must verify the proof.
Yeah.
So if you verify this proof the way it is, it will not pass. Okay, let's just verify and see whether it passes before you do that. Let's just verify, and let's to verify the proof, you enter contract.
Yeah. Contract. Yeah.
And after entering contract, go to Go to that read me, and we have yes, we have that forge test. That is how we verify the proof.
This one.
Forge test. Yes, yes. Okay, run it. Now it has failed.
So it encountered one failing test.
And you know why it has failed? Why it has failed? Let me show why it has failed. Go to test, just above Cyprian verify.app. There is some test inside contract. Inside contract.
Oh, inside contract. Okay.
Yes, we have test there, just inside contract. We have test, yes. Yes, that one. Now, at that starter.sol, look at the second line. The second line.
The second line.
12th line. 12th line.
Oh, okay. This one.
12th line, I've said we have only one public input. Change
here.
that to 2.
Okay.
Yes, change that to 2. Okay, now come to line 19. Come to line 19. Copy that line 19.
I copy this line.
Yes. Paste it. Paste that one below it.
I paste it.
Just below it. There. Okay, we'll put a semicolon. Now, the one you made to be public input was mod. Was it mod?
Let's see. Let's verify. It was yes. It was M. M is mod.
M is 17. Okay, go back there and write 17 instead of 6. Write 17 there. Okay. Now, let's generate a proof again. Let's go back to JS. Let's go back to JS, generate a proof. We must have a proof that matches our public inputs.
All right. So JS.
Have you generated the proof?
Let me generate it.
Yarn generate proof.
Yeah, it has generated. So
the proof is generated. Is that okay? Now go to contract and verify the proof. Because if the proof is correct, it will now pass. Go to contract.
Okay. Wait. It still fails the test.
Okay. There's no problem. Let's delete target.
Okay.
Delete target. Let's just go step by step. Target is deleted. Because that is where our proof is. Our proof is in target.
So it's looking at the same proof.
Yes, it's looking at the old proof.
Yeah.
Go to circuits. Okay, build.sh.
Yeah. Then
go to JS.
Then we do the yarn generate proof.
Yes.
And then we go to contract. And then we do the forge test optimizer. Okay, it still fails.
Let's now see what it's saying.
It says failing test. The test verify proof. The test verify proof. Which one is it? This one.
There's something there. Up. What is that? Okay.
Yeah, it fails
Make
the test
sure.
verify proof function. This one. Oh, wait. Oh, it's the Cyprian verifier app test.
Yes, just click on that. No, not that one. Just below the starter.t.sol in the test. Yes, there's that one.
Okay. So it failed the verify proof.
Okay, let me see where to change. You see the name must be where we have function verify equal that 2 bits. That 2 bits. But I can see it's generating. I don't know why it now says they're not equal. Let's just go back to starter.t.sol and see. We had changed proof. The public inputs to 2. Public inputs
we
are 2.
changed to 2.
Okay.
Then we added another one.
What you do, click that prover.toml.
Okay.
Let's see. Not prover.toml, the public inputs. Public inputs. Oh, that is 11. And this is 6. How is 11 coming?
I also don't understand because we have the M in the prover.yml is 17 and 6. And we've also put here as 17 and 6. So where is it coming from?
Let's go back to main. What did you make public?
So X, U32, EU32, mod M, which should be public, U32, and then Y, public field.
Okay, there's no problem. Let's go to starter.t.sol. Starter.t.sol. Where are you? Click on it. Okay, now the thing is, what I had forgotten to tell you is that this thing, you name them the way they appear. The way they appear. So in our main, M comes first.
Yes, M comes first before Y.
Then Y comes last.
Yes.
So that means in our starter.t.sol, that should be 17.
And then this one should be 6.
Yes, this should be 6. Yes. That is, I think I'd forgotten to tell you that. Now delete the target. It must now work. Delete our target.
Okay. So let's.
Yeah, so that is why it was getting 11 because it was subtracting now 6 from 17.
All right.
Yeah, they must be in the order in which they appear.
Okay. So
let's go to the circuits. Let's go to the circuits. Good. Let's go to JS. Yarn generate proof. Now, when you check your public inputs, they must now be correct.
Yeah.
Public inputs must now be correct. 17, then 6.
Wait, it still has 11. Yeah. It's not happening.
Okay. You had deleted it, huh?
Yes, I had deleted it.
Okay, let's go to contract and try and see. Let's go to contracts. Make that 11. Just make that 17, 11. We will see where 11 is coming, where 17 is coming from. Okay, go to contract and verify the proof. Just go to contract and verify the proof. We'll find out why 11 is coming in.
Compiling. So it still says
It
that
fails.
it fails.
Now the problem is, okay, write 17 there. Just write 17 there. The problem is I don't understand why the 11 is coming from. Write 17 and again verify, try and verify, just try and verify at the bottom.
It's still failing.
It still fails.
Yeah.
Okay, let's go back to our main.nr and see. Let's go back to main.nr. Okay, we made that be public and it rejects. Okay, delete the public.
Okay.
That two, that public, just remove it. But why 11?
Okay, let's see.
Okay, let's work with that.
Let's delete the target.
And then you must again change the starter.sol. Must change the starter.sol.
So
Just
we are
delete
gonna
the first line. Or just make it that 6 and delete the second one. Okay. Okay, that's okay. Oh, return it. Just return it. There's something we're not done. There's something we're not done.
What else?
Now look what public inputs. The first one is named 0. Not there, not there. Where we are currently.
Just here. Okay.
Yes, we have named that one 0 and then 0. Suppose we name 0 and then 1.
And then 1 because of the indexes.
Yes. So it's wondering, it's now trying to reach an amicable because we have the same value appearing twice differently. Supposed to be 0, 1, 2, 3 as you progress.
Wow.
Okay, let's go back to the main and return public and then, yes, there. Okay, let's now again do it. I think that is where the problem was. Because we had named it twice, the same thing, different, some different things named the same. You're inside circuit, huh?
Yes.
Field or research.
Then go cd into JS.
Get JS. Yeah, is it a good thing when you fail, you learn?
Yeah.
Yeah, there are many things you then get to learn when you get something wrong.
Generate proof and then we cd into contracts. Yeah, it has actually passed all of them. One test has passed.
Yes.
That was the problem.
There's only one test. That was the problem. We named the same two different things. So now look at the public inputs.
And it's just a small thing, but it can cause you a problem. But it's still 11.
It's still 11, eh?
Yeah.
Did you delete it?
Yes, I deleted it. I deleted the target. But let's do it again.
Again, do it. But you can see it as the proof has been verified.
Yeah.
Now check starter.sol. Starter.sol.
Yeah.
That is 17. Is that okay?
Yeah.
That is 17. Huh? Okay. Do that process again.
Okay.
Do it again.
And then generate proof. And then ready into contract.
After Yan generates, you can check your public inputs and see what they are inside target. Inside target, yes, public inputs.
Still 11.
Still 11.
Why is it 20? Yeah.
Okay. So let's do this. Delete target. Delete target. Do Nago compile.
In the circuits.
In the circuits. Good. Do a build. Good. Go to JS. If the target is not correctly deleting, then we will, I think we will try remove something. There's a command to remove it. Do yarn generate.
Yeah, I've already done it.
Okay, what about the target? Look at the target again and see what public inputs are there.
Still 11.
Yeah, so I think what is supposed to happen, I don't know whether it's remove target. So there's a command for removing a target. Because there's a time you can remove it and then it doesn't really go anywhere. It just disappears from here, but it's just you can still remember it. Can still remember it. So I think it's remembering. But okay, so there's something you've learned when you are naming your elements inside starter.t.sol. They must be, of course, in the order in which they appear. If M comes first, just try to reverse. Just try to reverse. Let's go inside that is starter, and again, make 6 to come first. Make 6 to come first.
Okay.
Put yes. Make 6 to come first.
And then
17. And then let's again try and see if it will compile.
So we delete target as well. And then and generate. And then we go to contracts. So it has failed.
Yeah, it fails.
Yeah.
They must be arranged in the order in which they appear. The problem we have in the target is that the system is remembering the old target. There's a way you delete it completely, then regenerate it. I don't know whether it's RM target. Try RM target inside circuits.
Inside circuits, right?
Yes, try RM.
Okay. RM target.
It's not the command, is that okay? But there's a command for it.
There's RM, RF. I think I know that.
Yes, it's that.
Yeah, it's that one.
That's deleted, yeah?
Yeah.
Now repeat the process and let's see.
Okay, so we start by doing build.sh. All right, and then we go to.
Oh, just a minute. Return the value the way they were, the way they're supposed to be inside our 17. Then
oops.
Okay, make another value. Let's forget about 70. Let's forget about mod because I think mod will. Let's make another element to be public instead of m.
Okay. We can make
So that one, make it private and make e public.
Okay.
Okay, go to the prove atomil and see what e is.
E is 3. So
it's 3.
So
okay.
I change this to 3.
Yes. Okay. Okay, build.sh.
All right, so let me do build.sh again. Okay, let me first delete target because it was there.
You can just leave it. There's no problem.
Okay.
There's no problem. There's not even deleting it. There's no problem. Build.sh.
Yeah, I've already done that.
Go to
Lead it to JS. Then yarn generates. Yarn generate proof. Okay.
Check our public.
Yes, so we have 3 and 6.
Yes. I think the 17 had a problem because what is 17 for the 17? I think that is where the problem was coming in. Yeah, maybe I think that's where the problem was coming in. Okay, now can you verify?
Okay. So we go into contracts.
Yes, that's how we verify. If the proof is not correctly done, it will fail.
Okay, so
the command is in the README. Yes.
Here it is.
That is a command.
So, yeah, it has passed.
Okay. Now, there's one thing I wanted you to know. You've known about the starter.t.sol, what it does. You are defining the public inputs inside there. If there are 2, you're saying there are 2. If there are 3, you're saying there are 3. In that case that we had earlier, you had 1 public input and it was a 1. Just go back there and let's see.
Where to main or?
No, starter.t.sol. Starter.
Okay.
Yes. So you can see we have defined 2. New bytes 2. Yes. Now, there's that bracket coming before 2. That's a square bracket. Remove it and let's see whether it runs.
That's
okay. Can you confirm the proof?
Okay, so I verify the proof again.
Yes, verify the proof. Let's see whether it runs without that square bracket.
No, it says compilation failed. Yeah, contract or array type expected.
And it has highlighted where the mistake is.
Yes.
It has highlighted where the mistake is. Return the square bracket. Now, put a 1 inside there.
Yeah.
Yes. Verify the proof.
It has panicked. Array out of bounds access.
Encountered the 1 failing. Is that okay?
Yeah.
Then there's something it says.
Yeah. Fail
Yes.
panic array out of bounds access.
Yes. Okay, return to, because the problem there is the length. The length
Yeah.
of the proof expects that the proof has two public inputs, but you are forcing it to accept one public input.
Yeah.
It will not accept that. It rejects that. Go to the verify.sol. Verify.sol. At the top, what does it say? At the top.
Yeah.
Public inputs are two.
Yeah.
Okay.
Yeah.
Yes. So this is the contract. The contract has two public inputs. You cannot force it to verify a proof of one public input. It will not accept because they must agree. They must agree at every time. So the contract is saying that the number of public inputs are two. When it was run, we ran the contract by build.sh. So build.sh gave us the contract. You see, build.sh, we are running it in the circuits.
Yes.
And it's telling us that the contract has two public inputs. When we go to JS and we do our yarn generate proof, it generates a proof, and that proof has two public inputs. Yeah. So you cannot force now the verification to do one proof, one public input. Okay, return to starter.sol, starter.t.sol.
I already did this.
Okay, that's okay. One thing I wanted you to know is about generate proof.ts.
Yeah.
Generate proof.ts is inside JS. Inside JS.
Where is JS? Okay. Generate proof.ts.
Yes, that one. Yes. Now look at line number 13 up to line number 18.
Yeah.
Those are what we have in the prover terminal. What we have in the prover terminal is what we have just put here. You put anything else in a different order, and it will not compile. If you put anything else, or even change the order of the prover terminal, just check the prover terminal, the order of the prover terminal.
I changed the order.
Yeah, if you change the order, it will not. Just change.
Of the prover or of the generate proof.ts? Yes,
that where you are currently.
Okay. So maybe I make this 17. No. I think I can. I put E and M.
Okay. Just call that one M then. Just call that M and call and 17.
Okay. So I'm going to put this one over here. Not that one. I'm gonna put where's my
E3, then that one M17.
Okay.
Just delete the first line 14.
Yeah. Okay.
Okay. Generate proof. Yarn generate proof. Do yarn generate.
Let me be in JS. So CD into JS. Yarn generate proof generated successfully.
Okay. Okay, now verify.
All right. So CD into contracts. Verify it by this command. This one. Compiling. The test has passed.
Oh, okay. I think the order maybe the order only affects when the
I did not
alphabet,
save.
sorry.
Okay, let me save the file. Because as you can see here, I had not saved here. Mine I have to save manually by command
Oh,
save.
okay.
Yeah, let me now
Okay, okay.
try
In
again.
fact, if it's
Mhm.
wrong, generate proof will just show you. You'll see it change color.
Okay.
If it does not change the color, it means it has accepted.
Interesting. Generate proof.
If it's
It
wrong,
should.
it just change color.
It should change color.
It should change color. Like for instance,
Mm-hmm.
remove that comma after 3. Just remove the comma after 3 and save it.
Yeah,
It will change color.
Yeah, there's okay. Yeah, it does give an error here. Expected comma.
Okay, it has given, or for me to change the color, and you can see there's a 1 above. There's a 1. Just see where it is. Above, just above where I'm looking at the first line above there, where we have not inside here.
Here?
No. On the top, even there you can see there's a 1.
Yeah.
It means 1 error.
Yes, definitely.
Delete another comma again, even after 6. And you can see they have increased to 2.
Yeah.
So it's telling you there are 2 errors. So for me, it will become red. Mine will become red, and then it gives you the number of errors. Just look for where they are.
Okay.
Now, in fact, okay, just go up. We have okay. We have like where you are, just above it. Just okay. Not there. Inside.
Yeah.
Generate. Inside generate. Okay. Good. Now, the name of this program is Modular Noir Modular Exponentiation. Is that okay? And you can see it under import circuit from. We have circuits, and then target. Then the name of the program.
Yeah.
Change that name of the program, and you'll see an error.
Okay, let me just change it to like something else.
It has already indicated there's an error.
Yeah.
And how did it get it? It got this error. Now just leave it the way it is. Just delete. Just delete. Okay. There's no problem. That way. Leave it that way. Is that okay? It's telling you there's an error. Now, how does it know there's an error? It knows this because it's communicating with the Nagotomil. Yes, because this name is what is inside Nagotomil. Just go inside Nagotomil and do what you've done. You will see it accept. Just do the name there. What you did, just do the same thing.
Yeah. So
okay,
where was it? Okay, save this.
Okay, so you have done that. There's no problem. Have you written the same thing?
Yes, I've written the same thing in Nago.
The same thing, yeah? Now, the only thing that is making it count as one error now is then the target.
Yes, the target. Definitely.
Now do Nago compile.
Didn't it? Have to get out of here. Yeah, so it has changed to no.
Now the one is not there. The one is not there.
Yeah.
It's now saying there's no error.
Yeah.
Is that okay?
Yes.
Because the error was our error was on the name. Now we went to the Nagotomil and written the same name. Then now the target, and we did Nago compile so that we have, because what it's looking for the witness. This is a generate proof. For it to generate proof, it must have a witness. So its witness had a different name. So when the witness has a different name, it shows you that that is an error. So you must change and have the correct name. The witness have the same name.
Okay.
I think we can stop at that unless somebody has a question.
All right. Let me stop share. All right.